Hi, so this week we will recall on complexity. So the complexity itself is learned in last term in course analysis of complexity of algorithm. So this complexity is important in our course as well because mainly we want to construct an efficient algorithm. So we need to know complexity of an algorithm we want to construct. So first, what is the importance of complexity? This is the fundamentals of algorithmic problem solving. Uh, if we have a problem and we want to solve it, we first, of course, need to understand the problem. But instead of directly code the algorithm to uh, solve the problem, actually we need to decide on computational means, exact versus approximate solving, data structures, and also algorithm design techniques. So now we are focused on the algorithm design techniques here. After we have decided on these matters, then we can design the algorithms. And then if we already have the algorithm we want to use, we can prove its correctness first. If it is not correct, then we can go back to design it again, or even go back to decide the technique we will use. But if it is correct, we can go to analyze the algorithm. We ask ourselves if it is efficient enough to be implemented or not. If so, we can code the algorithm, or we redesign or decide again the technique we will use. Should we worry about the speed and amount of memory of our computer? Well, maybe if the problem we are facing is not big, so we don't really need much memory. Even if we have non-efficient algorithm, then we don't really care. But if we face a real life problem, then we may have a very big data we face. So of course, the speed and memory of our computer is really important. We can compute the time of our computer by this equation, where Tn is the running time we will need for execution, and C is execution time of algorithm basic operation on particular computer, and Cn is the number of times the algorithm basic ops need to be executed for the algorithm. So there are two kinds of algorithm efficiency. We can see efficiency with respect to time or with respect to space, but here we focus on efficiency with respect to time only. So we will not discuss efficiency with respect to space in this course. So assuming there exists the two sorting algorithms, insertion sort and merge sort, with the following complexity. How much longer will the algorithm run if we double each algorithm input size? If we know the complexity, we can we can have the approximation about that. So here, if we double the input size, so we will have four time longer, four times longer time to execute the algorithm. For merge sort, we will have it like this, so it is that not as bad as insertion sort. When we compute time complexity, we need to mind about input size. Almost all algorithms run longer on larger inputs. That's why we need to see input size of the algorithm. For example, if we want to sort some arrays, then the larger arrays we have, the longer time we need to implement the algorithm. Also, multiply larger matrix will result in much longer time consumed to implement the algorithm. To compute algorithms efficiency at first, investigate parameter n indicating the algorithm's input size. So for example, if we have sorting, searching, and the smallest element, what is the input size for these problems? Well, for sorting, we need to sort the elements we have on the list. For that, of course, we need to check all elements of the list. For searching as well, we need to uh, check each element of the list if it is equal to what we search or not. So it really depends on the size of the list. The smallest element as well, of course, we need to check every element we have on the list. So it will depend on the size of the list. So the input size will be the size of the list. For computing polynomials, here we need to do multiplication or addition as much as the highest order we have in the polynomial, or we can also see the number of coefficient we have here. So the input size is the polynomial's degree or the number of its coefficients. For product of two n by n matrices, of course, we need to see the matrix order n or the number of elements being multiplied. Other problems we can check for a spell checking algorithm, of course, it depends on the size of the word or sentence we want to check. So that is the input size. For checking whether a given integer is a prime, we need to check if n can be divided by numbers below n other than 1 and n itself. So of course we need to check n integer, n minus 1, but well, the size will be the n. Other thing that we need to consider when we compute time complexity is basic operation. Basic operation is the most important operation we have in the algorithm. The most time-consuming operation in the algorithm's innermost loop is usually considered as basic operation. Now, if we already have basic operation and we already have the input size, and to determine the complexity, we can count the number of times the algorithm's basic operation is executed on input of size n. So if we already able to compute the complexity of algorithm, we can do comparison analysis of two algorithms. So to do this comparison, we can ask what is the basic operation and how about their complexities and which of those algorithms is much more efficient than the others. For example, if we have this algorithm as the first algorithm, sequential search, here we have some operation. We have assignment here, and also you have assignment here and comparison here. We have checking condition here, and also another assignment. But here uh, we will consider the loops we have here. The question is, how many times do we need to go inside the loops in the worst case? So here we have the condition for the loops. The algorithm first assign 1 as position and check if the element in position 1 is x or not. If not, and 1 is still not larger than n, then we go to the loop. And we add the position by 1, and then we check again the element on that position, and if it's still not larger than n, so we check another position. So here we can say that in the worst case, we need to check n position if there is no x in a1 to an. So the worst case, we will do this n times. So we can say that it is n. We can say the complexity is n. And for the second algorithm, it's binary search. Here we consider a list. We assume the list has already sorted from the lowest element to the highest element. So, for example, we have a list on size n. The first assignment we have here, we assign this as low and this as high, and then we find the middle. We have mid here, and we check the element we have here. If it is equal to x, then the position, we store the position, so we will not get back to the iteration. But if not, then the position still 0 here, so we will check the low if low is still less or equal to high. But if x is less than a mid, then we will check this part, or otherwise we will check this part. So basically, first we have this size of Ri, but after we have mid, in the worst case, we still need to check, and we have half size of the previous Ri to check. And it will divide it again by 2 in the next iteration if we go to the next iteration, and divide it again by 2 if we go to the next iteration, and so on. So we can say that the complexity is in log 2n. So which of those algorithms is much more efficient? Here we have log 2n, and the previous one we have n, so it is obvious that the second one is much more efficient than the first one. Order of growth. Intuitively, if we have two algorithms, for example, one has quadratic time complexity and the other one have linear time complexity, which algorithm does eventually give efficient performance? Just justify the answer by providing the value of n0. So here basically we want to know if 0.01 n square and 100 n, we want to know how their relation is the left one is less or equal to the right one, or maybe more. We will check about that. So here we can multiply both sides with this, but of course, to be able to do this, we need to say that n is not 0. So here we will have n and 10,000. So here, n can be anything. It can even be more than 10,000. but here stay constant. So we can say that A1 is less than A2 for n less than 10,000, or we can say equal here, and A2 is mm, sorry, A1 is more than A2 for n more than 10,000. So the question is, which algorithm does eventually give efficient performance? So here we can say that A2 eventually after n equals to 10,000 will give um, efficient performance because its time efficiency is less than here, the time consumption. So here, based on the order, if it takes the same amount of time to process the basic operations, the algorithm A2, the second algorithm, is more efficient, for instance, larger than 10,000. By solving the inequality we have here, which is dividing both sides by 0.01 n, we can have that n larger than 10,000. So from the previous example, we can conclude that any linear time algorithm is actually eventually more efficient than any quadratic time algorithm. The keyword highlighted in this course is eventual behavior. This eventual behavior can be notated by three main notation. It's big O, big omega, and also big theta. The most used notation here is big O because essentially big O is talking about the worst case we have, but big omega is talking about the best case. We can see it like that, and theta is more like the average, something like that. But because we are more interested in searching the worst case, so big O is usually is more common to use. So if we see the graphic here, initially we have Gn, the blue line. Initially Gn starts out above Cfn, but eventually it falls beneath Cfn and stays there. So in this case, after some n, which is 0, Gn is always beneath Cfn. So for cases like this, we say that Gn is in big O n square because Fn is n square if we see C as 2. Formal definition of big O notation is we have a function Gn is in big O Fn if we can have a constant C and non-negative integer n0 such that for every n at least n0, this inequation holds. And then this is the graphic we have, so we actually don't really care what happens before n0. It even can be fluctuative like this, or it can also be G can also be very large at first, but we only care that after some point Gn is always beneath Cfn. So in this case, we can write that Gn is in big O Fn, or we can write it like this with equation equal symbol. Next, big omega notation. Basically, it is on we only see in the previous one we have gn eventually always below cfn, but for big omega eventually gn is always above cfn. So like the previous one, we don't care how gn behave before that and zero we have, but after some time, after some point, gn is always above cfn. That is what we care about in big omega notation. We can use the similar notation to say that gn is in big omega fn. And then for big theta, we want to know that after some point, we can have gn is always above C1fn for some C1, but it is also beneath C2fn for some C2. So basically, we can say that big theta, gn is in big theta if it is in big O, but it also in big omega. So for exercise, we can show if Tn we have here is in big OGN. I will show you how to prove it. Okay, so this is actually really simple. So we want to show that Tn is less or equal to C times N for some T at least N null from T equal to N 0 and larger. So here we can say that N is less or equal to N and 1024 is less or equal to 1024N. But of course it only holds for N at least 1 because it doesn't hold for 0. So this is equals to 1025N. So we can consider this as C and this as N0 so that we can say that it is in big O-N. The next one, here we have Tn equals to 1 plus 2 plus so on until N. We can also write it backwards. So we have it like this. And if we add them, we have N plus 1. We add it as many as N. So this is equal to N times N plus 1. So that Tn is equals to half of it, which is a half of n squared plus a half of n. Of course, this is less than or equal to this, and it holds for any n, non-negative n. So here we have n squared, so we can consider 1 as C and 0 as N0 so that we can say that Tn is in big O N square. Next one. Here we have, this is very similar with number 1, so we can say that it is less than or equal to 10n square and 4n is less or equal to 4n squared and 2 is less or equal to 2n squared, but of course it only holds for at least 2. Then it is equals to 16n squared, so we can consider 2 as n0 and 16 as c, so we can conclude that Tn is in big omega n squared. The next one. Here, okay, for this case, we need a lemma that n square is less or equal to 2 to the n, and it is holds for at least 6 and equals to 6. To prove this, we can prove by induction. I will not show the proof here, but you can do it yourself. It's supposed to be learned in mathematical logic already, so I assume you can do it. So here we have it less than or equal to this, but of course it only holds for n larger or equal to 6, and we still need to write this one. So this is equal to this, so we can consider this as c and this as n0, so that we can say that Tn is in big O 2 to the n. The next one, this uses the same lemma we have before, so this is equal to this, and n square is less or equal to 2 to the n, and it holds for n at least 6. So this is equal to 7 times 2 to the n, so that we have this as c and this as n0, so that we can say that Tn is in big O 2 to the n. The next one, we have Tn is 1 to the k plus 2 to the k plus so on until n to the k. For this, it is obvious that 1 is less than n, so we can say that it is less to n to the k. But of course, it only works for n at least 1 because it doesn't hold for 0. So this is then, we can write it like this, so that we have n times n to the k, which is equivalent to n to the k plus 1. So we can consider 1 as c and 1 as n0, so that we can conclude that Tn is in big O n to the k plus 1. The next one, we know that log a to b is equals to b log a, right? So here, this is equal to 3 log n, but because we don't have log 0, we can say that n is at least 1. And of course, we can consider this as c and this as n0, so we can say that Tn is in big O log n. The next one, we use the same properties we have before. So this is equal to 10n log 3 to the n, and it holds for any n. so that, oops, sorry, we don't need the n here. Okay, so we know that log 3 is less than 1, so it is less or equal to 10n. So we can consider n0 as 0 as n0 and 10 as c, so that we can conclude that the n is in big O n. And the next one here, we know that log n is less or equal to n. It is obvious by the definition of logarithm. So here we can say that it is less or equal to 2n plus 6 n, and it is equals to 8n. So we can consider 8 as c, and because this hold for all n not 1, we don't have log 0. So here 1 can be considered as n0, so that we can conclude that the n is in big O n. The last one, it is similar to what we have in number 6. So Tn is n factorial, which means 1 times 2 times so on until n. And because 1 is less or equal to n for n not 0, of course, so we can say it like this, which is equals to n to the n. So we have n0 and we also have c, which is 1. So we can conclude that the n is in big O n to the n. This is another exercise, but I will not go through all 9 of these. Here we only need to determine whether the assertions are true or false. Essentially, big O, once the function we have here is always beneath functions we have here at some point. So for number 2, we have n to the 5, and here we have n, so we already know that it is impossible. So we really can say that it is false. For the second one, we have 5 here and 17 here, so it should be true. And the fifth one, we have 5 here and we have n here for big omega. So for big omega, we essentially want this function eventually always above c times this function. We can see from the order, this is n to 5 and this is n, so it is really possible. So it should be true, but not for number 6. For theta, remember that a function is in theta fn if it is in big O fn and in big omega fn. Here, because it is not in big O n, so we can say that it is not in big theta n. And because it is not in big omega n to 17, so it should be false as well. But okay, sorry. So but here we are more interested in number 1, 4, and 7. For number 1, we know that 3 So for number 1, we know that Tn is 3n to the 5 minus 16n plus 2, and it should be less or equal to 3n to the 5 plus 2, right? Because here we have subtraction, but we don't have it here. So it is less or equal to 3n to the 5 plus 2n to the 5, and it works for n at least 1. And then it is equals to 5n to the 5, so we already have n0 and also c, so we can conclude that it is in big O n to the 5. And then for big omega, we have 3n to the 5 minus 16n plus 2. It is larger than something. So we need to think, what is smaller than this? Well, here we have plus 2 here, so we can only consider 3n to the 5 minus 16n, right? And this is equals to 3n to the 5 minus 2 to the 4 times n. So here, if we consider a larger part of this, we should have a smaller total value, right? So we can say that it is larger than 3n to the 5 minus n to the 4 times n. And of course, it only works for n at least 2. So this is equals to 2n to the 5. So here we already have c and we already have n0. So we can conclude that this is also true, because the function is in big zero, big O, and it is also in big omega, so we can conclude that it is in big theta. Next part, mathematical analysis of iterative algorithm. For example, we want to determine the time complexity and its asymptotic from this bubble sort procedure. Here, for iterative algorithm, we need to consider how many times we need to enter the loop. Here we have a loop here, and we have a nested loop, and how many times do we need to do the comparison? That is the question we need to know the answer to. So here, for the first loop, the outermost loop, I can be 1 until n minus 1. And if we have I equals to 1, we need to compare in the case where j equals to 1 until n minus 1. So the comparison will happen for n minus 1 times. If I equals to 2, then we need to check for, in the case for j from 1 to n minus 2. So the comparison, we do the comparison n minus 2 times, and so on, and so on until I equals to n, so that we need to check, no, n minus 1, so we need to check j equals to 1 only, so that the comparison only need to be done once. So we can add them and have tn. So tn will be 1 plus 2 plus so on until n minus 1. And we can also write it backwards, so that we can have 2tn is equals to n times n minus 1, which is equals to n square minus n. So that Tn is half of n square minus a half of n, which is of course less or equal to a half n square. So we can consider this as C, and it holds for any n. So we can have it as n0. So the asymptotic for this algorithm is in big O n square. The next one, we want to determine the time complexity and its asymptotic again. So here we study the algorithm first. So basically, this algorithm is an algorithm to multiply x and z, which return the value of x. So we have 0 as x first, and if 0 is larger than 0, if z is larger than 0, we check if z is odd. If so, we add y to x. If not, we double the w, and we divide z by 2. And we do this loop as long as z is larger than 0. So here we can consider 0 to z first, and in the next iteration z value is divided by 2, and then in the next iteration it is also divided by 2, and so on until we reach 0. So we can see from this pattern that the algorithm is in big O log to n. For recursive algorithm, it is a bit tricky because we need to see the recurrence relation of the algorithm, and also we need to know how to derive them and how to solve them. So this is the big picture of recurrence relation. So recurrence relation always have a base of recursion. So what is the base we have that might happen to the recursion? And what is the running time for that case? And otherwise, we have a recursion call, and how many times we do that recursion call, and what is the size of that recursion call. And maybe we also have other operation we have in the case of non-base case. So for example, if we have this algorithm that can compute x to the n, so basically x to the n is x times x until n times, but we can see it as a recursion of x times x to the n minus 1, and this is x times x times x n minus 2, right? So here we have when n equals to 0, then we directly return to 1 and return 1. And for other case, we multiply power x comma n minus 1 with x. So the basic operation for this algorithm is obvious. It is multiplication we have here. So the basic operation is multiplication. For the case of n equals to 0, here we don't have multiplication at all. So Tn is equals to 0. But for other case, we have one multiplication here but we also have recursive call, and the size of it is n minus 1, because here we have n, but here we have n minus 1. So this is the recurrence relation we have for this algorithm. And the question is how to solve it. How do we know which big O it's belong to? We can solve the recurrence relation using substitution. So we know that from the relation that for all n bigger than 1, Tn is 1 plus Tn minus 1. And from this relation, we also know that Tn minus 1 is equals to 1 plus Tn minus 2. So we can substitute this to 1 plus 1 plus Tn minus 2. And we can also substitute this again to 1 plus Tn minus 3, and so on. So we can have it like this. So this is the substitution for Tn minus 1, and this is for Tn minus 2, this is for Tn minus 3, and this is for Tn minus 4. So from here we can see the pattern. When we have 5 here, we have 4 here. We have 4 here, we have 3 here. Now back to the function we have before, we have the base case is n equals to 0. So here we want to have n t0, so that we need to subtract n with n, so that we can have n minus 1 here. So this is equals t0, which is equals to 0. N minus 1 plus 1 is n. So we can have tn equals to n, which means that it belongs to big O n. There's another type of recurrence relation we have, something like this, but actually it also means that n is in form of this for some non-negative integer k, of course. And also this n is 3 to the k. For this also n is 3 to the k. This is the same, and this is also the same, like this. So we can know it from the division we have here. Okay, so next I will not show you how to solve all 6 of these. I will only show one of them here. So how we can solve them? Back to the previous slide, we know that n is 2 to the k for some non-negative integer k. Okay, so from this recurrence, we need to notice for this recurrence we have t n per 2 is equals to 2 t n per 4 plus 6 times n per 2. So we can substitute this to 2 t n per 4 plus 3n plus 6n. And the 6n is from here. So this is equals to this, and we can write it like this. Right. So we need to substitute again. T n per 2 to the 2 is equals to 2 t n per 2 to the 3 plus 6 times n per 2 to the 2. So here we substitute this to 2 to the 2 times 2t n per 2 to the 3 plus 6 n per 2 to the 2 plus 2 times 6n. And this is equals to 2 to the 3 tn per 2 to the 3 plus 3 times 6n. So we can consider m equals to 1, and we have this. We can consider m equals to 2, and we have this one. And when m equals to 3, we have this one. So what happens if we have m equals to k? So for this case, we will have 2 to the k times t n per 2 to the k plus k times 6n. And this is equals to n because we have this. This is equals to n, so that we can have n t 1 plus 6kn, which is equals to n plus 6kn, because we know that t1 is equals to 1. And from here, we know that k is log 2n. Okay, so that here we can say that it is equals to this, right? And of course, it is less or equal to n log 2n plus 6n log 2n for n at least 2, right? So we know that this is in big O and log 2n. Okay, so that's all for this week. This is the reference you can use if you want to read more about the topic this week, and see you next week.